Hi, welcome back to this course on computational thermodynamics and kinetics of materials. Let's continue with the more application of thermodynamics to materials. We have seen about Gibbs energy composition diagram in the last class. Today we will see more about that, how tangent construction helps in understanding equilibrium and how phase equilibria is dictated by Gibbs energy composition from GX plots and reading tie line data from Gibbs energy composition plots and ultimately how Gibbs energy composition plots can evolve into phase diagrams. So this is one simple Gibbs energy composition curve for a phase phi, and this G versus X plot is drawn at a fixed temperature and pressure for a crystal structure. So this crystal structure here is very important because one Gibbs energy composition plot is plotted for every crystal structure. If we see multiple phases competing for stability, we will have a curve for one crystal structure. Example, this phi phase can be a BCC phase. So this is a binary system AB. Take this A and B, two different elements. Both are in phi structure, meaning both are BCC. And once they form the solution, that is also in BCC structure. So in this case, if you take any composition like this, so this is something corresponding to this, about 25% of B. What will be the Gibbs energy? You can directly read it from here. This is the Gibbs energy value of phi at this composition. How does that come? You know, it is basically the weighted average of chemical potentials mu A in phi and mu B in phi. Now, what are these? These extreme points here and here. This is Gibbs energy of A in phi structure. This is Gibbs energy of B in phi structure, meaning the pure elements are in this particular crystal structure, BCC structure. Now you may wonder, why is it important? The point is, the element A may be in nature an FCC element. In that case, the Gibbs energy of pure element A you cannot get directly. Okay, so because at this temperature, we are fixing the temperature, right? So at this temperature, A may be FCC and you can't get the Gibbs energy of that. In that case, can we draw this kind of curve? The point is, yes, we need to get this data, only then we can draw this curve up to these extreme ends. So at some combination it may be in phi structure, doesn't matter, but A may not be in pure form in phi structure. But we need to have the Gibbs energy of A in phi structure in order to put this point here, this green curve, as long as it reaches this pure A end, it should have the data for that. So we need to have Gibbs energy of A in phi structure or BCC structure in this case. How do we get that? We will see that in the future. Now about another structure alpha, here it is alpha labeled as FCC. Let's say A and B are considered in FCC structure now, and they mix and form AB solution again in the same structure. If this is the composition, where do we mark this is the Gibbs energy composition curve for alpha curve, and this is GA in alpha structure, this is GB in alpha structure, and this point here will be the Gibbs energy of the solution. Again, this is nothing but the weighted average of mu of A in alpha structure and mu B in alpha structure. We will see one important idea now, combining these things. Let's say some temperature T1, we consider alpha and phi, these two phases have this sort of G versus X curves. And in this, we will do something called a tangent construction to understand what phases will be in equilibrium. Now, consider the same composition here. If at all, let's say alpha is stable somehow, okay, I mean alpha is seen, will it be stable? At this composition, will alpha structured solution be stable? Just by looking at the curve, you may say phi is below alpha, so Gibbs energy of phi is below. Therefore, phi should be more stable, the lower Gibbs energy phase. That is right. In this case, it is quite straightforward. But if multiple curves come, their positions are here and there, it will be difficult to read which is below what and what will be the most stable phase. So in that case, there is this tangent construction method that is going to help us. Let's see how it is done. At this point, we are going to draw a tangent to alpha curve. Okay, this composition, overall composition point in alpha curve, we are going to draw a tangent there and check is there any other phase Gibbs energy curve being lower than that. You see this green curve is completely below this line. Therefore, this green curve, meaning the phi phase, is going to be stable. That's how we have to figure it out. So what are we doing here is checking will alpha be stable at 25% B. What do we do? Draw a tangent to alpha at 25% B and check below the tangent of below this tangent G of any phase occur anywhere or not. Okay. And here we see phi phase occurs almost throughout the entire composition range. Therefore, phi will be stable. So lowest Gibbs energy phase phi is stable. That's what we are seeing it here. So obviously when we have these two curves competing for stability, we will have phi being the stable phase for the entire composition range, not only for the 25% B, for the entire composition range. So if we do see the atomistic picture from left to right, from pure A it can become pure B without changing the structure of phi, because phi is the stable state throughout this composition range. That's the atomistic picture. Now, if we go to some other temperature T2, what happens at that temperature is these two curves intersect. It's no more one phase being dominant throughout the composition range. Now, these two phases intersect. How is the phase equilibrium understood in this? Consider this composition here. Okay. Here you see this phi being stable, being marked here, and if we draw a tangent to that and check is there any other phase Gibbs energy curve lower than this, we don't see anything else. Therefore, we can conclude phi will be the stable state here. And these are the chemical potentials of elements in that. So this is phi stable structure, and more or less this composition is tracked to this about 75% of B, more orange atoms and less blue atoms. So below the tangent, G of no other phase occurs, therefore phi is stable. Now what about this composition here? Okay, A rich composition, draw a tangent there to alpha. You don't see any other curve below this, therefore you can conclude alpha is the stable state here. So this is the alpha structure AB solution. Right. So below the tangent, G of no other phase occurs. Right. Now this composition is quite interesting. If you see at this composition and try to make any one single phase stable, you will be in a trouble. See that. Now if we put the dot here, you may tend to put it here thinking that this is the lowest. We will do that also. Now let's first put it in this phi curve. Okay, and think that whether phi can be stable at this particular composition or not. So draw a tangent and see that this alpha curve is below that, right? Alpha curve is below this tangent. Therefore, this single phase phi cannot be stable. That is the conclusion. So this phi cannot be stable. Okay, below the tangent, G of other phase occurs. That is the alpha phase now. Now, let us put the dot in the alpha curve and draw a tangent there, and we will see that there is this phi phase curve occurring below the tangent of alpha phase. What does it mean? Phi phase is also not stable. Okay, so this is alpha, and alpha below the tangent we see G of other phase occurs, that is this phi phase Gibbs energy. Now, ultimately what will happen is, if you draw a tangent like this to these curves, actually it is tangent common to both the curves. This is the common tangent construction. I am putting it here, common tangent construction. That is going to give the equilibrium phases at this composition. The equilibrium phases I am saying because more than one phase are going to stay in equilibrium. So let us mark the Gibbs energy of the phase here. Gibbs energy of the composition here, not Gibbs energy of the phase. Gibbs energy of the overall composition here. So this is the composition, this is the Gibbs energy of the entire system now. Now what are the phases inside? Wherever the tangent touches the Gibbs energy curves. Here it touches alpha curve, here it touches the phi curve. So both these phases will stay in equilibrium. And this will be the chemical potential of A and B in the system. Okay. So this is how two phases occur. Alpha and phi both will stay in equilibrium. This is what has happened. Below the tangent, g of no other phase occurs. Here we see that below this tangent, no other phase occurs. Tangent is common to two g curves. Both the phases exist in equilibrium. The points where the tangent touches, that indicates the equilibrium compositions. Okay, this point here, if you drop it down, and this point here, if you drop it down and read those points in the x-axis, that is nothing but the tie line data which we have seen in the phase diagram. Okay, so this tells you what are the compositions of these two phases that are staying in equilibrium. Right. Now recall equilibrium criteria. We said chemical potential of an element is the same in both the phases in equilibrium. Okay, I hope you could connect that and think here. Mu of A is same in both these phases. That's the meaning of tangent touching both the phase curves. Okay. Now, what is the range of this two-phase phase equilibria from this overall composition till this overall composition? We will have these two phases in equilibrium, meaning the Gibbs energy will be minimum only when two phases exist in equilibrium and not a single phase. And beyond this composition or before this composition, let's say this entire range here or the range before this pink dot here, this entire range, both of them will have only single phase. This side it will be phi, and from below this point it will be alpha. Okay, only alpha will be stable, not two phases. And only in overall composition of this range will possess this two phase equilibrium. Right. So for a range of composition, two phases exist. Before and after this range, single phases exist. Now let us take this tie line data that we have seen to the phase diagram. Okay, so this is our temperature T2 where two curves intersect, and we see for some composition, overall composition range, we know there will be two phases in equilibrium. What are we going to do is take these compositions, these two compositions here, the x-axis, they are labeled here, and this is the temperature T2, right? And when we put a phase diagram, what we put temperature in y-axis and composition in x-axis, right? So this composition data should go against this temperature to this diagram. That's what we are doing here. At temperature T2, these 2 points are labeled here corresponding to the x values in this axis, and that is the tie line. Okay, what does tie line say? It says two phases are in equilibrium and what are the composition of these two phases, alpha and phi in this case, and before this point it is alpha that is stable, after this point it is phi that is stable, right? So if we put some kind of a colored thing for phi also, should not be actually done, but just to indicate this is a phi phase region, this region is alpha phase region. Okay, so if you go to temperature T1, we know what is stable. From left to right, it is only the phi phase that is stable. So if we take temperature T1 and label phi throughout the entire composition range, phi phase is stable, right? Now based on all this understanding, we will plot G versus X at different temperatures and then take the data from that to T versus X, that is the phase diagram, and see how a phase diagram evolves from that ultimately. In this case, we are considering solid and liquid, two phases. At temperature T1, you see liquid is stable throughout compared to solid. Liquid has the lower Gibbs energy for the entire composition range. And if we plot temperature versus composition, then we will see that liquid will be the only stable phase all along the composition range at T1. Okay, so this is temperature T1 and it is completely liquid. Orange means liquid, right? Now at another temperature T2, we see solid and liquid intersecting. Therefore, we will have to have this kind of curve now. Okay, so there is a two phase region coming here, and at temperature T3, which is a lower temperature, we see solid being stable throughout. Let us mark that here. At T3, solid is stable. Now what if we refine these temperature intervals and go for many temperature points here and see how the Gibbs energy curve is? Possibly there are more intersection curves like this near this temperature, and they all will give us multiple points like this. right? So these are the tie lines, two-phase informations. Okay. If we connect all orange dots and blue dots with the lines, we will see an isomorphous phase diagram evolving. Okay. In this case, the region here in the top is all liquid being stable from left to right. Beyond this orange line in the right side, it will be single phase, and below this blue line, it will be all solids. So now this region, entire region is a single phase liquid region. This region is single phase solid region, and this dark region is liquid plus solid region. So we get a nice isomorphous diagram coming from G versus X plots. So this is how very elegantly this Gibbs energy versus composition plots at different temperatures can be used, and to see how thermodynamics underpins the phase diagram. Okay, so we have seen how to make the binary phase diagram, right? Isomorphous phase diagram. We have seen how to make that completely through experimental manner, that is using the cooling curve method. Take a sample, take multiple compositions from left to right, take them to very high temperature, cool them, track where the liquid to solid transformations happen, and then take those points from cooling curve, temperature versus time curve, to the phase diagram. That's how we have constructed it experimentally, right? So in this case, you see same isomorphous diagram has come, but completely through thermodynamics. Okay, this idea is what the CalFed tools or the computational thermodynamics tools are going to do. That way, this lecture has a lot of implication throughout this course. So in the next couple of class also, we'll spend on these Gibbs energy versus composition plots and try to do some exercises also. Right, thank you. I hope the lecture is useful. I'll see you in the next class.